So hello out there in Enzyme land. Thank you so much, everyone, for joining us for this virtual event. My name is Jake, and I will be your host. Today, we are talking about enzyme intelligence. This is the core of Ginkgo's protein engineering technology as it applies to enzymes. Part of enzyme intelligence is artificial intelligence, so machine learning. I think everybody in this call is already hip to the news that machine learning is a very powerful tool for protein design, and we agree, we see it too. But for us, it's the machine learning algorithms are just part of the story. So to really deliver on enzyme engineering, you've got to bring the computational design tools, you need the human experts to pilot them, and you need the high quality data to feed them. And then if you're really smart, you want to do it all in a commercial strain that's ready to take your enzyme downstream and produce it at scale. So discovery, optimization, manufacturing, Ginkgo's Foundry brings all of that together. So that's why I'm excited for this event. And I've got someone else here who I know is also very excited to kick us off. Let me introduce a man who loves enzymes, the co-founder and CEO of Ginkgo Bioworks, Jason Kelly.
Thanks, Jake. And I do love enzymes. So yeah, I mean, I'll just give a quick minute on Ginkgo because I know there's a lot of folks on this call that may not know much about us. So we're company's about 1,200 people based in Boston. We took the company public last year, raised about $1.6 billion. And if you come visit our labs in Boston, you'll hear about this today. You'll see a lot of robotics and automation, a facility that between the technology investment and physical scale of it, we've invested close to $500 million into that facility. And just to be clear, all that money we raised last year, we don't put it towards developing our own therapeutics, our own agricultural products, our own chemicals. What we invested in is that infrastructure so that we can enable our customers to develop great new therapeutics or chemicals or agricultural products or other biotech products. And so I do think now is actually a really exciting time to be partnering in Ginkgo because we're in a great position to keep scaling that infrastructure. We just announced this week that launching Ginkgo Enzyme services, which you'll hear about today. We also did a large deal with Merck earlier this year in this enzyme space, Aldevron previously, and work with a number of large companies like Bayer and others who ultimately need biocatalysts in pharma, ag, and chemicals. We've added more customer programs in the last quarter than any previous quarter at Ginkgo. And like I said, we're capitalized to scale, so I think it is a good time to partner. The last thing I'll point out, and you'll hear about this today, is if you're in the biopharma space, the simple way to think about our business model is we operate like a CRO. In other words, you can outsource your research to us on a contract basis. So if you need more of it, you spend more, you need less, you spend less. There's variable cost R&D spending in this area that can often be something that can really help out sort of the economics and managing your R&D spend. But the key idea is we want to be a CRO that offers you something that you can't get anywhere else. And so I do want to pass it along to the team now, the sort of Ginkgo Enzyme Services team, and Emily sort of leading the way here to show you some of the things that we have that we think are differentiated that you can't get anywhere else. And these are all available as a service for you today. So thanks for joining us.
Amazing. Thanks, Jason. So that's kind of a lot to get to. So let's get to it. Here is today's agenda. So we've introduced Ginkgo's offering. Coming up next is the main event. This is a presentation from our enzyme engineers about how we do it. What is enzyme intelligence and what can it do for you? That presentation is going to be organized around case studies of recent enzyme engineering projects that were executed here on the Foundry. Then after that, we're going to take your questions. We've got an all-star team of BD reps on hand to answer all your questions about how do you get your project on Ginkgo's Foundry? What does this offering look like for you? What's your menu of options? How's it going to work for your application? And then, of course, if we do our job right, you're going to want to connect with our team and get the power of the Foundry working on your enzymes. So we'll offer you those ways to get in touch. And in particular, it's enzymes@ginkgobioworks.com. Now, here's the people who are going to help you do it. Today on the call, we've got Cindy Chang, Alyssa Blaze, Jesse Dill, and Sneha Srikrishnan. These are the folks who are ready to answer your questions about the Enzyme Services offering, who are ready to connect with you when you're ready to take that next step. And then on the technical side, we've got Nathan Schmidt here today. He's a senior protein engineer here at Ginkgo with expertise in biophysics, structural biology, and protein design. And for today's main speaker, we welcome Dr. Emily Wrenbeck, our head of protein engineering. Emily joined Ginkgo in 2017, and since then she's worked on many projects delivering better protein designs. She's also led efforts to expand Ginkgo's platform capabilities, particularly in computational protein engineering and protein experimental workflows. Before that, she did her PhD in chemical engineering with Tim Whitehead, studying biomolecular recognition and protein molecular evolution. And with that, I will hand the floor over to Emily Wrenbeck. Take it away, Emily.
Awesome. Thanks so much, Jake. And I'm very excited to share a little bit with you all today on one facet of our end-to-end enzyme services offerings, which has to do with the discovery and improvement of enzymes for our customers. And so our approach to enzymes includes both a broad computational toolkit for designing large enzyme libraries, shown on the left, as well as a world-class bioengineering foundry capable of building and experimentally testing these large candidate enzyme libraries, among other things. And so what's fundamental here when we think about enzymes is that ultimately why we value enzymes in industry is for their incredible functions and ability to catalyze desirable reactions at process-friendly conditions. And so function is the key sort of element here that has informed how we've built our platform. And so on the left, the tools in our computational toolkit are geared towards what we would call functional design. And on the right, we take a data-first approach to enzymes. So in essence, we let the power of real wet lab data be the gasoline in our design tank, if you will, so that for one, we ensure we're optimizing for the right thing. And for two, we want to ensure that we are testing a sufficiently scaled library size to enable discovery of rare or new functionalities. And so our foundries have been designed with innate flexibility to really scale our ability to support a diversity of wet lab protein assays in a high throughput way. And so to give a quick overview of the computational toolkit, on the top here for enzyme discovery, we are experts in the sourcing of metagenomic libraries of natural enzyme sequences from all kingdoms of life. And so we search across available public sequence databases as well as a number of proprietary databases. And so here with the sourcing and testing of libraries of natural enzymes based on some prior knowledge or expert opinion of which families might be fruitful to source from, what we're really doing is taking advantage of the promiscuous nature of natural enzymes to catalyze functions for which they did not necessarily evolve for, and certainly which they are not annotated for in databases. And so for enzyme optimization or to inform sourcing campaigns, we leverage a breadth of best-in-class computational tools for protein design, sort of including the bleeding edge developments with self-supervised learning models for protein design, molecular dynamic simulations, and Rosetta, along with custom software and algorithms we've built in-house to automate and streamline much of these workflows such that applying them in a standardized and expedient manner is possible. And so finally, when more than one round of optimization is required, we routinely follow a machine learning guided protein design approach. And this is done with a platform we refer to as OWL, which enables us to learn from the massive data sets collected in the foundry to inform the next round of design. And so a little bit on the namesake here, owls hunt by night and are able to find their prey in the dark. And so that's what it can feel like sometimes when engineering enzymes, especially when we're hunting in the dark. And so what we're doing with OWL is applying machine learning directly on experimental data sets and training models to help us see answers that might otherwise be non-obvious to either a protein engineer's intuition or to more traditional design tools. And so in essence, what we do is let the data be our guide. Okay, and so just to zoom in a little bit more on how OWL is working, since it will be referenced in the case studies to follow. So in a typical iterative workflow, a protein variant library design is made using a number of computational tools, and we'll call this sort of a Gen N library. This library is then built and experimentally tested in the Foundry to generate assay-labeled data sets. And so now we have a data set where we have a set of related but slightly perturbed protein sequences from the library, along with their performance data or how well they behaved in an experimental test. And so you have a protein sequence to performance data set. And then we use OWL platform to train a suite of supervised models and optimize their performance with the goal of having the models learn the sequence to activity relationships. And now these models are used to design new protein sequences. And so we take these predictions, design a new library around them, and we'll call that a Gen N+1 library and build and test them as before. And when this is working, what you see is that the predicted performance from the model correlates with the actual performance observed experimentally. And I can't stress enough that what's critical to make this work is having data sets of sufficient quality as well as size, as scale does matter such that the model can actually learn meaningful relationships about the enzyme. And that's where the beauty of Ginkgo's experimental Foundry comes in to supply the gasoline for our design engine. Okay, so now I'd like to share a few quick vignettes of customer case studies to show how our enzyme discovery and optimization platform works in action. So to start, I want to share a quick story about why automated high-throughput experimental approaches are essential to achieving the discovery of enzyme functions from metagenomic libraries. And so this was for a customer that wanted to produce a specialty chemical in a microbe via metabolic engineering. And we needed higher performant enzymes. And so to tackle this problem, Ginkgo searched our protein databases for those related to an initial seed enzyme over here from a plant. And so on the left, what I'm showing is a two-dimensional representation of the sequence space resulting from this search, where the dot proximity or how close a dot is to another one indicates the relatedness of the sequences. And so our starting seed and highly related enzymes are shown here on this right island. And so we collected some sequences there. And as well, we did further searching to expand the sequence set beyond the starting island so as to sample biological diversity more broadly. And so based on these search results, a library of 2,000 enzymes shown in dark blue were built and screened for the desired activity. And only a single hit, highlighted in orange and very different from our starting seed enzyme, had the desired enzyme activity. This hit then formed the basis for a second round of in silico search and sourcing more densely near this hit, resulting in a round 2 library, which is colored in green. And this was built and screened as before. And from this round 2 library, we found several dozen more active enzymes in this concentrated cluster. And so in summary, it's often advantageous to cast sort of a large, broad net first, especially when the chemistry is expected to be rare in nature, and then follow up with more focused libraries, which densely sample around hits. And so this result isn't unique to this project. In many cases, the best performing enzymes are highly dissimilar to the starting seed enzyme, and in some cases down to less than 30% sequence identity. And again, the ability of the Foundry to build and test these large enzyme libraries is what makes these kinds of rare discoveries a routine outcome at Ginkgo. Okay, so coming off the heels of a large metagenomic discovery campaign, where we've typically identified a set of better starting enzyme templates than the original enzyme, we can now shift into protein engineering. And so related, depending on the application, sometimes there may not be a great solution to a customer objective within naturally occurring proteins, or a customer already has an enzyme that they'd like us to work from. So in these instances, we would also turn to optimizing existing enzymes. And so for this case study here, I am showing an enzyme critical to a customer project where they need to improve the overall activity. And so for this case study, this particular enzyme is a rather large homodimer and is recognized in literature for being recalcitrant to enzyme evolution and engineering. The enzyme also exhibits a multi-step reaction pathway, mechanism rather, with unknown rate limiting step, which further complicates the application of hypothesis-driven design. And so we opted for an iterative, data-driven machine learning guided protein design approach with OWL. Okay, so To improve this enzyme, we engaged in 4 successive DDTL cycles. And so in early rounds, we used a combination of sequence-based self-supervised model predictions, structural docking and design, and targeted saturation mutagenesis to explore the sequence activity relationships. And in addition to arrayed activity testing, the breadth of expertise at Ginkgo afforded us the opportunity to also develop ultra high throughput pooled experimental assays for screening both functional properties as well as abundance on large libraries, which complemented the array testing data. And so in successive rounds of engineering, these data were used within OWL to achieve further improvements, culminating in a 10-fold improvement in KCAT over KM for this enzyme. And of note, when we look at the overall effectiveness of performing hit recombination with OWL by integrating these large Foundry-generated data sets with supervised learning, we find this approach provides a significant population of variants with improved performance. Okay, so going beyond the discovery and activity optimization challenge, we can also optimize properties like product specificity. And so in this case study, a customer's biosynthetic pathway contained a terpene synthase enzyme that only produced the target molecule as less than 10% of the product profile. And so similar to the prior example for this difficult enzyme optimization task, traditional rational design approaches struggle because they lack predictive power to suggest what mutations would improve the product specificity. And so again, hunting in the dark. And so we took the approach of iterative DDTL cycles and learning directly from the experimental data to inform our designs with OWL. And so Ginkgo developed high throughput GCMS methodology to measure each of the 5 different possible products. And after 11 rounds of iterative engineering, where we iteratively utilized informed sampling and supervised machine learning, we were able to improve the product specificity to greater than 75%, with an overall performance increase of 8.8-fold relative to the starting parent enzyme. Okay, so we're not always afforded the opportunity to conduct iterative rounds of improvement, but rather we must aim to achieve the engineering objectives in a single round. And so to close out this section of the talk, I want to share a case study of improving a biocatalyst used in API manufacturing, where in a single round of engineering, we were able to improve both enzyme speed and specificity in industrially relevant process conditions. And so a customer was already using an enzyme in a biocatalytic step for the production of a small molecule API and needed help improving their synthesis to hydrolysis ratio, which is depicted here, with the ultimate goal of reducing manufacturing costs. And so this enzyme had previously been engineered and was being used in production, but there was desire for further performance gains. And so we leveraged a suite of computational tools to design a single enzyme variant library containing about 1,100 members. And so on this little insert here, I'm just showing one facet of this library design approach, where we used the learnings and insights from molecular dynamic simulations to focus our protein engineering efforts. So for one, we used MD to upgrade the 3D structural models by refining them. We also identified critical regions by studying the correlation of movements of each position to those we knew to be important for catalytic function. And finally, we utilized the MG trajectory output to obtain an ensemble of conformations that was used in structure-based design workflows. And so these MD insights were combined with other prediction tools to ultimately design a library of 1,100 variants. The candidates were then tested in an assay that Ginkgo developed to closely mimic the conditions of the API biocatalytic manufacturing process, because we wanted to identify only commercially relevant variants. And so after one DBT round, we identified variants with a 5-fold improvement in specificity for synthesis over hydrolysis, and variants with a 6.5-fold improvement in overall enzyme speed. And so these improved enzymes are currently being tested by our customers, by our customer at commercial scale. All right, so finally, to wrap up, I will briefly touch on the other end of our end-to-end enzyme service offerings. So for biocatalysts, the host expression of the enzyme and optimization of the conditions to manufacture it can have a major impact on the ultimate process cost. And so to address this, we can leverage our host strain engineering capabilities, as well as fermentation and other process optimization expertise to improve enzyme titers and manufacturing performance. So to share a quick case study in this vein, early on in the pandemic, we realized that production of the Vicinia capping enzyme was going to be a critical bottleneck for manufacturing of mRNA vaccines. And so we worked to develop improved expression systems in E. coli, as well as fermentation process conditions to improve VCE titers. And the outcome here was that our efforts led to a 10-fold improvement for Aldevron's manufacturing scale of VCE. And so again, no modification to the VCE amino acid sequence was done. Rather, the 10-fold improvement was realized solely through host strain engineering and optimization of the fermentation process conditions. And so while the majority of biocatalysis projects today happen in E. coli, not all enzymes can express and fold well in E. coli. And so we have a number of optimized fungal strain assets, including Pichia pastoris and Aspergillus niger, that can produce large titers of enzymes. And so our Pichia strains and expression systems have demonstrated a 20-fold improved performance relative to industry standards. And I should mention that we've invested significant research and development into these strains to deliver both high performance in terms of titer, but also the ability to do both methanol and methanol-free production. And so finally, we have also powerful assets in Aspergillus. And so this includes a low viscosity strain, as typically Aspergillus that are used to produce heterologous enzymes get all filamentous and gummy in reactors, which limits their ability to grow to high densities and therefore produce significant enzyme titers. All right, so today I showed you a small snapshot of the kinds of work our teams can do with enzymes today. And I should note that the work presented today represents the efforts and contributions of dozens of amazing scientists across Ginkgo. But I wanted to close by showing just a quick snapshot of the breadth of different classes of enzymes we have worked with already across dozens of different projects. So this plot represents just a couple of years worth of enzyme projects where the rows here represent the EC or enzyme classification number, and each sort of colored stack indicates different customer program. And the length of the bar, the x-axis, shows how many experimental samples we have tested for that class of enzyme. And so takeaway is that we've already spanned a wide breadth of enzyme functions in terms of actually designing, building, and testing them in the lab. And we'd love to chat with you all about your enzymes and add them to this growing list. And so with that, I will conclude, and I think we are going to do some Q&A now. Thanks, Jake.
Yay, all right. Thanks, Emily. Yes, that is going to bring us to the Q&A portion of today's program. And so for this, I'm going to ask my fellow panelists to go cameras on. Yes, amazing. You all look great. So for this session, I'd like to introduce everybody to the little Q&A button that you've got at the bottom of your Zoom panel. Some of you have already been using it, so that's great. So you can type your questions in there, and we'll do our best to answer them. How it works in Zoom is that you won't be able to see each other's questions until there's an answer. In the interest of time, we probably won't be able to answer all the questions on camera, but we're going to be busily working behind the scenes to give you written answers too. So if the panelists look distracted, it's not because they're checking their email; it's because they're giving you text answers in the Q&A bar there. Okay, so how I'd like to run this is I want to start with a couple of technical questions for Emily and Nathan. But I do want to make sure that we have time to get to the business side of these end-to-end enzyme services. So if you're interested in enzyme services, Now is a good time for you to start filling out your questions in that Q&A panel, and we'll get to those in just a few minutes. Okay. So let's see. Okay, so to get us started, for the VCE case study, the question is tenfold improvement, tenfold result seems pretty large. Is this just the result of strain design and process optimization? And how routine is this result?
Yeah. So I think to start, like typically in the field of biocatalysis, we're sort of hyper-focused on the enzyme properties like Kcat, Km, inhibition constants, smelting temperature, tolerance to solvent, aggregation propensity, et cetera. And we treat enzymes like, a protein is a protein is a protein, but we often neglect just how important the host strain design and handling can be in getting the most bang for your buck when it comes to manufacturing. And so at Ginkgo, part of this, the approach here relies on how we've chosen to standardize and curate the expression parts that we're using. So in essence, we apply more of an engineering mindset to the actual biological parts, design parts that go into the host strain design. The other is considering what host to actually work in. So instead of just going not beyond E. coli, Ginkgo has experience working in dozens of distinct species and has thought a lot about the process for how to onboard new species to genetically manipulate them and evolve these hosts so they're more tractable to work with. As well, Ginkgo has strong expertise in synthetic biology to build next generation systems for expression as well as next generation hosts. So a great example of this is sort of the methanol-free expression system we built for Pichia, along with just better Pichia chassis in general, that can really push the limits of heterologous protein titer. And one last note here is that we've invested a lot in the ability to run sort of high throughput prototyping of fermentation process conditions. And it's pretty routine for us to see pretty big gains in either protein titer or in the case of small molecule producing engineered enzymes, we can get big gains in terms of the molecule titer from just doing fermentation process optimization alone.
Cool. Okay. Yeah. So I guess my takeaway from that is that there can still be a lot of work to do, even if you've got an exact enzyme sequence, even if you can't change your enzyme at all. There's still a lot that can be done to improve the production.
Yeah, you just need to be considerate of the production host and how it's handled.
Cool. Okay, I got another technical question here. This is how does metagenomic sourcing relate to protein engineering approaches in practice? When do you decide to do one strategy versus the other? Maybe this for Nate. Yeah, that sounds like.
Yeah. I think I can take this one. Hello, everybody. I'm Nathan Schmidt, protein engineer at Ginkgo. So the question is, when does it make the most sense to use metagenomic sourcing versus protein engineering? And I would start out by saying it's not necessarily an either or. However, you can start to think about it in terms of limiting cases, in terms of what you might want to use one versus the other, such as there are situations where there aren't really any well-known enzymes that can perform a specific reaction or biocatalytic process, then it usually makes sense to start out with metagenomic sourcing in this case. Now, assuming that we do discover an enzyme that can do this reaction, I think just sort of thinking about it, you can imagine that the likelihood of it being optimized for this function is quite low, right? This is probably more coming from things like enzyme promiscuity, and then this enzyme itself evolved within an organism that could be very different than the one that you're using for your synbio application. And so for this reasons, you can really think about this as being a starting point for optimizing and improving it using protein engineering. And so in cases like this, we often start with metagenomic sourcing. And then once we find something, we move into protein engineering to really improve the performance of the enzyme, whether it's expression, turnover rate, substrate product specificity, and so on. More broadly, I think it makes sense to talk about this in terms of fitness landscapes and sequence similarities. So, metagenomic sourcing, as Emily referred to during her talk, it gives you homologs that have sequence identities that can be quite low, 20, 30% or so. Looking at, enzymes from perspective of protein engineering, if you have like a 500 amino acid protein, if you mutate 50 positions, using point mutations, you still have a homolog with 90% identity. So, one way of thinking about this is metagenomics sourcing provides a sampling of what nature has to offer. And this allows you to kind of like make these bigger jumps around in your sequence landscape. And that can help to get away from things like local maxima, within the landscape as well. And this is, kind of a way of getting away from these local maxima that is much less likely to happen with many types of protein evolution. Protein engineering is much more of kind of a dense sampling thing where you're improving it by sampling closer to the starting point. And so you can really think about enzyme discovery and optimization as a search space problem, where MS is kind of this coarse way that you jump around the landscape. And then once you find something, then you go ahead and use protein engineering to further optimize, because most enzymes are not going to be have activity that's selected for the specific application that you're going to use. But again, these aren't mutually exclusive. Both of them use both sequence and structural information. You can at the very least apply the learnings from one to another. We've had situations where hits from metagenomic sourcing will collectively have some type of general feature that once you have sort of analyzed it and understand what that feature is, you can use that knowledge and then apply it within protein engineering. We've done the opposite as well, where you take beneficial mutations and if you do it correctly, you can transfer them into sourced sequences and receive benefits as well. And then this kind of gets into, I would say, like hybrid approaches as well. Like, why not do both of them at the same time? And I would say that this is a very likely future state for us. However, you really need, bigger and more complete data sets to get like these highly complex relationships between sequence structure and function. And so I guess you could envision, such models, these deep predictive models being able to do this, but you need larger amounts of data, things like code base being a game changer for these type of situations.
Cool. Very cool. Yeah, this idea that you might find something with 30% sequence similarity to your original target that is better performing, it blows my mind. It just absolutely changes everything that I thought I learned about enzymes in grad school. I'm used to thinking about 99%, 95%, and more than that, it's just a different universe. But I think so. This relates to a question here that I'm seeing. When you search public databases, are you mostly using sequence similarity? Have you used one or more of the new language model embeddings?
Yeah, I mean, I think there's a number of different ways to go about it, doing the searching and as well as the sampling, right? So we're going to take whatever method makes the most sense for the given project. So that might touch on sort of more quote unquote traditional things, which if you're a purist, you might actually classify as machine learning, and some of the newer, more novel machine learning approaches for both the searching and for the downsampling.
Cool. Oh man. Okay. I'm seeing a lot of really good questions come in. I hope that we can get to some more of them in the chat, but I want to start to move on a little bit here to make sure that we have time to talk about the business side. So I've got, this is a transitional sort of question. So what are Ginkgo's capabilities for enzyme production and scale up? So what happens after you found the perfect enzyme, you've done your metagenomic sourcing, you've done your sequence optimization, what happens next?
Yeah. So, I mean, it's a great question, and because, and this kind of underscores one of the ways in which Ginkgo likes to partner with companies is in an end-to-end sort of fashion. And so we will carry forward a project to the point at which it is ready to transfer for you, the customer. If you want bench scale proof of concept and then to hand things over, then that's great. We can wrap up the project there. We have, however, partnered all the way through to pilot scale, like proving out a process at bench scale, optimizing it, carrying up through pilot scale demonstrations, and then also coordinating a tech transfer and even helping with troubleshooting down the road, because we as a business succeed when the products succeed. And so, we make sure to partner with you up to the level that makes sense for your business and for that product.
This is a question for you, Emily. A question about your screening toolkit. I could see you screen more than 1 million variants in some cases. What screening technology do you use for those large libraries?
Yeah, great question. So we didn't get to dive into that too much today, but we do have some capabilities when it comes to what we call internally multiplexed assays for both protein function and abundance. And so for function, these might be sort of biosensor enabled or encapsulation enabled, as long as they've got a readout that's multiplex enabled. So if we can put them through a FACS sorting machine, for instance, or something similar. And then we also have sort of multiplex assays for just measuring protein abundance too. So in those scenarios, the readout is like an NGS sequence count, right? Which is pretty scalable, right? It can scale up to sizes of millions of diverse, millions of unique and protein sequences. And so often what we'll do is, like, if we can develop one of those multiplexed assays, we'll sort of do that in parallel with arrayed traditional activity-based screening. And it's a nice complementary data source that we can use to sort of feed in new diversity into arrayed library designs.
Very cool. Okay, here's another one. What if I like my organism? What if I have an organism that makes an enzyme and I don't want to change my organism? Can you work with my host organism? Sneha, maybe that's a question for you.
Yeah, I can take that. So absolutely, yes, we can work with your organism. We generally have the ability to work with most organisms out there in the industry. We have methods that we can use specifically geared to strain improvement in your organism of choice. The organisms that Emily presented are standard protein enzyme producers in industry that we have developed and built over time. We have a lot of tools associated with these organisms, but we also have other tools that we can employ and use for improving strains that we didn't present on today. So short answer, yes, we can. Yeah. Cool. I will also mention a couple points here while we're on it. For improving on strains that come from you, we have capabilities around adapted evolution, as well as encapsulated screening that can allow us to work with a multitude of filamentous fungi, different kinds of bacteria, and these are capabilities that we will use.
Okay, so now transitioning to more of a question with a business focus. I'm seeing one here. What types of different models do you use when partnering with a client? How does this differ between a large multinational company versus an early stage startup? And I might sort of just piggyback on that to ask, like, what does the process look like of partnering with Ginkgo? How do we do that how do we do business deals? And I think Alyssa, that sounds like a question for you.
Sure, I can start with kind of what the process looks like. So you'll work with teams, representatives from a few different teams here at Ginkgo. You'll touch our business development team, our deal team, our technical solutions team, and eventually alliance management and our program team. We'll have a few initial meetings, get to understand your enzyme target and your success criteria. After that, our technical solutions team will come up with a proposal to outline a technical plan as well as pricing, and we'll work closely with you to make sure that that proposal meets all of your goals. Simultaneously, our BD and deal team members will work with you to come up with the broader collaboration framework. And as Jesse said, our philosophy here is we win when you win. And the commercial structure typically involves payment for R&D services and also downstream value when you achieve commercial success. And then once the deal is signed, you'll be assigned an alliance manager and a program lead who will be working with you and dedicated to your team throughout program delivery. And that's kind of like the larger overview of how that'll work.
Great. Okay, I see a related question here. So this is, what is the business model for enzyme engineering, e.g. Fee for service or licensing? And I know, Cindy, I know that's something that you wanted to talk about.
Yeah, absolutely. I'm sorry, I was answering a Q&A question. So I'll stop doing that for now.
There's a lot of questions coming in.
Yeah, it's like a waterfall.
I love it. Keep them coming. Keep them coming.
So with regards to IP, our standard approach is really that Ginkgo owns the IP, but we give our customers what they need as far as an exclusive license or non-exclusive license for their commercialization. So we are not a CDMO or CRO only in the sense that we take on really tough projects. We want those tough enzymes and we engineer them and we create a tailored custom fit for you and then offer a non-exclusive or exclusive license to our customers to use those enzymes for their commercial needs.
Very cool. And can you maybe just give some examples of some other projects that we've worked on recently, just to give a sense for like the breadth of the kind of projects that we do?
Oh yeah, okay, so let me just start out by saying that we have run over 100 million enzyme tests in the past about 2 years. So just like sink that number in, 100 million enzyme tests over the past couple of years. And those enzymes are very, very widely, but I would say ones off the top of my head are some transglutaminases, proteases, RNA polymerase. We have some very nice work on RNA polymerase right now. I would be across the enzyme classes, we have enzymes represented in all 7 classes, all EC numbers.
Wild. All right, I got one. Here's one. All right, here's one. Pretty straightforward. How much does it cost? How much does one of these programs cost? Jesse, I'm gonna give that one to you.
All right, thanks, Jake. So I mean, the cost and timeline of a given product, of course, flex according to the nature of the work that needs to be done. And we generally recognize that, for customers, time is money, but so is money as well. And we will often structure an early phase of work to get some early proof points with an accordingly sort of lower price point to provide for an easy on ramp, verify that we're going in the right direction, and then ramp up accordingly with the second or sometimes even third phases of a given program. So, we will generally start with a 4 to 6 month starter program, and then ramp up from there. The cost itself, really varies according to the nature of the work, so I can't give like hard numbers in that case. But we will generally work with you, the customer, and just establish like what's the right level of scope of that initial project to fit your budget, and still deliver some promising proof points.
Very cool. Very cool. All right, and so related to that, how long is it going to take? How long is it going to take to get me this enzyme? Sneha, that sounds like one for you.
Yeah. So this is going to be tied up with what Jesse just mentioned, right? The cost and time go hand in hand. And what I will mention over here is it really depends on what the targets are that we are looking for. So if it's discovery, our discovery and evolution cycles can take anywhere from 3 months on the lower end, including DNA synthesis, right? So DNA synthesis included, all the way up to 6 months, depending on what organism is used for expressing these enzymes. Then we have the next stage, which is about, so once we've discovered the right sequence, we have the right functionality, comes the stage about scaling the enzyme in terms of producing lots of it. So now it's more a strain engineering question. And these strain engineering cycles can happen in small packages or small bodies of work, which cap at around 6 months. Sometimes it goes up to 8 months, depending on what organism is used. And so I would say that even for strain engineering, it would be a range between 4 months on the lower end, maybe 5 months to 8 months, depending on organism. And then finally, when it comes to process development or fermentation development, we would take anywhere from 2 to 4 months to find the right process that matches with the protein to be stable and to produce in the right organism.
Okay, so this is another sort of project design question. This one's a little bit more technical. How many engineered variants are considered when you start with an enzyme sequence? So, e.g., starting from a protein with a known crystal structure and using Rosetta/design, do you go after the top 5 or the top 100 or the top 1,000 variants? How do we think about that kind of technical decision? When do we do small number? When do we go big?
In terms of like how we decide what the composition of the library will look like, I would imagine this would be
the composition of the library during a sequence optimization.
Yep. So often in like the context of a first generation library, so what we'll do is we'll perform like kind of an initial assessment on like the available information we have for that particular enzyme, right? Like how good is the structural information, right? Is there a crystal? Is there a crystal with co-crystallized with a ligand of interest? How rich of sequence information can we get to build MSAs to train models on? And so that can inform how we might weight different strategies in the final library composition, right? So we might choose to forego structure-based design if we don't have a good structural model, right? Like you don't really, if you can't get a good structured model, then doing structure-based design might be a fraught sort of endeavor. But I think in general, what we like to do is sort of take forth a number of different strategies in a first generation library, because we don't know actually what's going to be the most effective. And with the bigger library sizes that we're afforded, we can do that, right? So we might, include a mixture of techniques in a first generation library. And so depending on how to slice and dice that mixture is going to depend on how good or how confident we feel in the sort of information going into each of those design approaches that we're taking.
Is it okay? I'm gonna put in one of my own questions, and I know I'm not supposed to do this, but I can't resist. Does it take a lot longer to do, like, if you're gonna do 100 variant library versus 1,000 variant library? Is this
no?
Like, what's
really?
that?
No, because usually what you get is, you score a bunch of variants and then you're sort of filtering by a threshold, right? So like if I use one, variant prediction scoring method, let's just say for point mutations, I can score them all, and then I can give you a library of 10, 100, 1,000, like in the same amount of time. So, and we've really tried hard to make the platform be such that like doing these more quote unquote rational approaches, right, isn't like a barrier to entry. Like we've tried to automate a lot of and codify like a lot of the best practices so that it's pretty quick to apply them on a new project.
Okay, I got another technology question here. Have you been able to use the power of continuous directed evolution to improve enzyme characteristics, either as a standalone approach or to further improve designed enzymes? I don't know if we mentioned directed evolution approaches in this talk. The question goes on, I would imagine a limitation is coupling the target enzyme activity to the growth of the platform cells. So do we do continuous directed evolution?
The short answer would be we do adaptive evolution, which is in some ways continuous, evolution, but stressed by the target or the by the goal that we have to achieve. So yes, we do have that capability to run these experiments, but it really depends on the organism we're working with. That is the condition. So Jake, you're absolutely right. as long as the organism and the protein are compatible with the conditions of evolution and fermentation, we should be fine.
Cool. Very cool. Okay, I think so. This is one that Cindy touched on earlier, but I think it's an important one. So maybe we circle back around to it. The question is, who owns the IP resulting from my project?
Well, that's a really interesting question. So generally speaking, if we're doing discovery and then we're doing protein engineering and then we're doing like the full gamut, Ginkgo is going to own the IP. Of course, if you have existing IP, customer X, with a protein of interest, you own your background IP. So we don't take that in any way. So long as we're playing within your IP circle, then we cannot own that. However, if we're doing the metagenomic mining from the beginning and finding the starting point and then doing the protein engineering and doing the scale up, our standard terms are that Ginkgo owns the IP and exclusive or non-exclusively licenses it out to the customer.
Cool. And then, so I guess, so related to that, is it possible to pay for service with an agreement of Ginkgo to not file IP on the deliverables?
I think that's a case-by-case basis, and there are reasons not to file IP, absolutely, and would love to engage with you, whoever this person is, and discuss why that would be a good strategy.
Yeah, that's an anonymous one, but do reach out if you want to follow up on that one. All right. Oh, here's one. So, do I have to manufacture the enzyme myself, or can I just buy the finished product from Ginkgo? Maybe that one's for you, Alyssa.
Sure, I can take it. So we do provide test samples during the development process, but what we'll actually do is partner with CDMOs for scale up. If you don't have an existing CDMO partner, we can help you find one. And we regularly transfer our processes to CDMOs at the 1,000-liter plus scale, and have also transferred to GMP facilities.
All right, so we are getting close to the end of time here, and I just want to make sure that we sort of wrap things up cleanly. I actually don't know what happens to the Zoom questions when we end the event. So what I'm going to do is I'm going to sort of ask the panelists to hang out for a little bit longer. Maybe we'll go cameras off, but I just want to make sure that we any sort of text-based answers that we're wrapping up. I want to make sure people have time to read them. I don't know if they're going to be lost forever, and it would be a shame. So after we close out the event here, I'll just ask people to stay on and keep doing text Q&A until we've done all we can do. If you need better enzymes, if you need some end-to-end enzyme services, so the email to reach out to is enzymes@ginkgobioworks.com. So this is your call to action. This is the best way to get in touch with us. Tell them Jake sent you. You'll get a discount, maybe. I want to thank everybody from our team who came out to answer questions today. Cindy, Jesse, Alyssa, Sneha, Nathan. I want to thank Emily for a very cool presentation, and of course for leading a lot of the work that was behind us. Also thanks to Jason Kelly, our CEO. I know he's excited about connecting with many of you personally, getting the Foundry working, just throwing the power of this Foundry behind your enzyme problem. And especially thank you to everyone who came out. You can expect follow-up emails from us with the recording from this event, and we look forward to hearing from you. So until next time, let's grow. Bye-bye. Maybe while we're waiting, I'll share a little personal story about enzymes. I got one. Somebody asked me the other day, do I have a favorite enzyme? Do I have a favorite enzyme? And I feel like I should, because I'm an enzyme guy. And so I'm thinking back to graduate school. And I remember my first enzymology classes when I learned about the carbonic anhydrase, and it just blew my mind. It's a mind-blowing enzyme. Do you know this enzyme? So this is the enzyme. It converts CO2 and bicarbonate, and they call it a perfect enzyme. Perfect enzyme because it's diffusion limited. It's as fast as an enzyme can possibly be, like 1 million turnovers every second. And it's so fast that it's like, so like when you drink soda, even the CO2 release, it's slow in the glass, but when it hits your mouth, it gets faster because of the carbonic anhydrase activity in your saliva. Amazing enzyme. Okay, that's my enzyme story. Check the
That is amazing.
check the count here. All right, looking good. I think people are mostly loaded in here. So hello out there.